I think I'm going to start recording now. So somebody might have a question. I mean, we can start now if someone has a question. So I'm not very good at listening, and I'm even worse at reading minds. So we're going to need a question in the chat or a statement in the, or just an actual statement if you unmute yourselves. What I did manage to do, however, is I managed to, I just dragged something apparently. See if I can undo the drag. Well, all right. So let me make this bigger. I figured out how to get the iPad working again. I called Apple and they were no help. It turned out the right thing to do was to turn the iPad off and then back on again, and then it worked. So maybe I'll just go on talking about general relativity. And someone has a question, I can address the question. So once again, it's based upon two of Einstein's ideas. The first one is that we don't know what system of coordinates is correct. And so we should write our equations as tensor equations so that they're the same in all coordinate systems. As we'll see, and as I think we saw yesterday, if you have an equation in a tensor equation written in one system of coordinates, then the same equation automatically is true in every other system of coordinates. The same tensor equation is true. So it's coordinate independent. The second of Einstein's ideas about general relativity is the equivalence principle, according to which the physics of special relativity holds inside a sufficiently small, freely falling laboratory in an arbitrary gravitational field. So if we imagine that this is a laboratory and there it's freely falling, well, the physics that applies inside that freely falling small lab is the physics of special relativity. And the way I think about this is that physics exists independently of people and of our coordinates. And when we change our coordinate system, the physics remains the same and the points remain the same. It's just that our description changes. And so we need to have a description that is in terms of tensor equations so that it's the same in all coordinate systems. So that was one of Einstein's ideas. And of course, his second idea was the equivalence principle, that if you're in a freely falling coordinate system, as long as the region you're talking about is small enough so that gravitational field is homogeneous in that region, then then the coordinates of a freely falling system suitably small so as to fit in that region, those coordinates, in those coordinates, the equations of special relativity hold. And one of the simpler things in tensor equations is something that's the same in all coordinate systems. This is called a scalar. If it depends on space-time, it's called a scalar field. And one example of that is the distance, or the squared distance, between points separated by dxi, where I goes from 0 to 3 if we're talking about our universe as opposed to somebody else's that might have more coordinates. And that's given by gik of x dxi dxk. And this is a scalar because it's the same in all coordinate systems. Now, how is it the same in all coordinate systems when we've got all these coordinates here? The idea is that the metric of space-time compensates for the different separations in different coordinate systems. So that's what's going on here. The metric of space-time is a shock absorber that occurs in tensor equations in such a way as to make them the same in all coordinate systems. And in a suitably small freely falling laboratory, special relativity holds. So the metric is the metric of special relativity, and the squared distance between points separated by dyi and the lab's coordinates is this. And so that's dy dot dy, or a to ik dyi dyk summed over I and k, or equivalently dy dot dy minus the square of dy0 squared. Let me just grab these sum signs that I forgot to put in. I wanted to put them in here. So that's because I hadn't yet talked about the summation convention in sufficient detail there. Well, that makes that equation something of a mess, but well, there's nothing to be done about it. Anyway, contravariant vectors, well, these separations are basically the definition of contravariant vectors. Partial derivatives are what defines covariant vectors. And if you have the gradient of a scalar, well, that's a covariant vector. You can have so a scalar is a tensor of rank 0, a vector, whether contravariant or covariant, is a tensor of rank 1. Tensors of rank 2 have 2 indexes or indices. If they're both lower, then it's covariant, both upper, it's contravariant, and we call it mixed if one is up and the other down. And you can extend these definitions to find things of higher rank. Of course, the summation convention that I've sort of been using all the time and explained in chapter 12 is this. The Kronecker delta is a mixed second rank tensor. It's also something that's invariant under changes of coordinates. So one of Einstein's ideas then is you must write the equations of physics in tensor form. It turns out that the homogeneous equations of Maxwell and Faraday were already tensor equations, and the four of them can be written this way. You pick one of the four numbers, 0, 1, 2, or 3, and put it aside, and then you let ijk be the other three numbers in the set 0, 1, 2, 3, and you get an equation of this form. And there are four ways of doing that. So these are the four homogeneous equations. They can be written in a fancy way in form language like this. Now, the inhomogeneous equations then are, for example, Gauss's law is one of them, and the other three, I forget what they're called, but they're written this way, namely that the divergence of Fik is basically the ith derivative of AI minus the kth derivative of, well, did I say that right? The ith derivative of AK minus the kth derivative of AI. In other words, it's E or B depending on what I and K are. And the divergence of that is the current density. And when I is 0, it's the charge density, and this is Gauss's law. G is the absolute value of the determinant of the metric of spacetime. And so this is the covariant form of Maxwell's equation. So what you see here is that these equations, which were derived by Maxwell, Faraday, and others around the time of the Civil War in the US, these equations are, half of them, two of them are completely general and apply in general relativity, or I should say four of them. The other four are almost of the same form as they apply in general relativity. The difference is simply that you get a constant, or well, not a constant, square root of G on this side, and then you have the square root of G that you have to differentiate here. Einstein's equations, well, anyway, these things then are true in all coordinate systems, to the extent that they're true in any coordinate system. Einstein's equations for cosmology in terms of how space and time vary or respond to the density of energy and momentum, or the energy momentum tensor, the response is very small, because you can see here we've got Newton's constant, which is a very small constant. And then you divide by the fourth power of the fastest speed in the world. And so you get something that's pretty small. And then this is then the Ricci tensor and the curvature of space-time. This one here, the Ricci tensor, is essentially a trace of what's called the curvature tensor. And these are discussed in section 1337. And so the idea is if you can write a physical law in one coordinate system as GJL of x equals 0, then in any other coordinate system, it'll be G prime IK of x prime, and that will also vanish because G prime IK of x prime is a linear combination of the GJL of x's, and these all vanish. So the thing vanishes in other coordinate systems. And so a theory written in terms of tensors has equations that are true in all coordinate systems if they're true in any coordinate system. By the way, the professor who was, I wouldn't say he was embarrassed, but he was surprised by my friend's remark that every equation is the form something equals 0. That's, by the way, why this is very important. You can take any physics equation and write it in the form something equals 0. And if this is a tensor equals 0, then it's automatically true everywhere. This professor's name was Sidney Coleman, or is Sidney Coleman. He unfortunately died young, tragically. but he was a spectacular lecturer. And of course, a great physicist. Anyway, once again, the principle of equivalence is that if you have an arbitrary gravitational field, well, and you have, if the gravitational field is homogeneous over some scale, which might be very small, but typically for gravity is very large. For example, the gravitational field that we're standing in, you and I, if we're both in Albuquerque, then we're all in Albuquerque, then the field to a large extent is pointing down, and it's the same here as it is where you are, or almost the same. Anyway, to the extent that if you're in a region where the field is uniform or approximately uniform, then special relativity applies. And, oh boy, there's a mistake. Let me fix that right away. One of the troubles with these computers is that when you write something in LaTeX, it looks so neat that it looks right just because it's neat. Anyway, in a freely falling, suitably small frame, special relativity applies. And so you can write the invariant quadratic distance, or the squared distance between 2 points, is then this is what's given in special relativity, and it's dy dot dy minus dy0 squared, and that's then the same in any other coordinate system because it's a scalar, and one can then just explicitly change from the y's to the x's. So dyj is partial yj partial xi dxi, and dyl is partial yl partial xk dxk. And so now what we've got is an expression here times dxi dxk. Well, that's the metric of spacetime. So the metric of spacetime is basically a sum of products of partial derivatives of the coordinates of the freely falling lab with respect to the coordinates that you're talking about, that you choose to use, your x coordinates, and that gives you gik of x. And we interpret that gik of x then as the gravitational field that was causing the laboratory to fall freely in the first place. So obviously you can have tensors that are symmetric or tensors that are anti-symmetric. And as I said, the Maxwell field tensor is anti-symmetric. You can I use in this book, the chapter in relativity at least, I used common notation for derivatives. In other sections, I've used subscript notations for derivatives. And when you use common notation for derivatives, then you use semicolon notation for covariant derivatives, which we'll get to shortly. One of the things that I think it was Gauss, maybe it was Riemann, but anyway, one of the great mathematical physicists of the 19th century showed was that you could just, for example, you could determine the shape of the Earth, or the geometry of the surface of the Earth, just by measuring distances between different cities. And you'd see that here, let me now actually use the, okay, now, why that is a funny color, I don't know. Well, it's, so let's suppose you had here New York, Miami, and San Francisco, and you measured that distance, you measured this distance, and you measured this distance. Well, if these were all flat in a plane, then there would be a relation between the squares of these distances. In particular, if you had a city 1 here, a city 2 there, and then a city 3 here, and this was a right angle, then obviously this distance here, C13 squared, would be equal to C12 squared plus C23 squared. If this is a right angle now, I unfortunately picked San Francisco, New York, and Miami, and this angle here is kind of a right angle, but it's by no means an exactly right angle. Anyway, what you do in reality then would be to, what Gauss, I think it was Gauss, showed was that if you measured all these distances between different cities, you'd realize that you were on the surface of a sphere, approximate sphere, of a certain radius. And so his point was then that you could discuss the geometry of closed, geometry of curved spaces in terms of the metric. Let me get back to the metric. In terms of the metric, and you didn't need to say, well, this Earth surface is actually a sphere in a three-dimensional space, and it's convenient to view it in a three-dimensional space. So that was an important advance. In my opinion, mathematicians and physicists, especially physicists, just took that idea to heart a little too strongly, most of them, and said, well, we can't say that we're embedded in a higher space-time, that's bad thought or bad think. And so I don't think that's right. I think it's possible and useful, and in fact mathematically true, that you can take any reasonable space or space-time and embed it in a higher space of higher dimension that is simply Euclidean, or, as I'll say in a moment, semi-Euclidean. And if we do that, then what we can imagine is that any point in space-time with coordinates x, well, first of all, it's a scalar because it's physical, so it's got to be the same in all coordinates. P prime of x prime is P of x prime, and that's P of x no matter what system of coordinates you use. So if P is a scalar, then its derivatives with respect to our coordinates are then covariant vectors, because partial derivatives of scalars are covariant vectors. And so if we change our coordinates, then the E's transform this way, which is the way that way covariant vectors transform. And moreover, we can say if we change our, not if we change our coordinates, but if we change the values of our coordinates a little bit by dxi, then the point we're describing changes by ei dxi. And of course, we can sum over that. And so these are basis vectors. And the way I think of it is, so here, let me switch. So we've got some sort of a curved space, and this one might be E1. And then we might have, unfortunately, I've drawn this in such a way I can't figure out quite how to do E2. Let's say E2 is going into the board, so maybe that's E2. And so that's basically the picture. Or equivalently, if our space is a two-dimensional space, you pick any point on the surface of the space and you imagine a plane, a plane that touches at that point, then it'll be parallel at that point to the surface, and that's called the tangent plane. And these vectors are called tangent vectors or basis vectors. I don't know why the hell I added this sentence. I think maybe I'll take it out. Now the simple case is what's called a Riemann manifold, and a Riemann manifold of dimension D, well, it's a space that locally looks like D-dimensional Euclidean space, and that is smooth enough for the derivatives that define tangent vectors to exist. So this is the archetypical case is that three-dimensional space is the archetypical case is the surface of a sphere of radius, say 10 centimeters, and that surface is a Riemann manifold of dimension 2, and it locally it looks like two-dimensional flat space, and the surface of the Earth is also a Riemann manifold, and it's locally two-dimensional on scales less than a kilometer. And of course, we normally think of a sphere as embedded in the three space that we're familiar with, and so too our Earth is a two-dimensional surface embedded in three space. And the fact is that the Nash, in fact, about 70 years ago, proved that every Riemann manifold can be embedded without change in shape in a Euclidean space of suitably high dimension. In the case of the sphere, it's a two-dimensional surface embedded in a three-dimensional Euclidean space. It turns out the mathematicians have shown that if it's an arbitrary Riemann manifold of dimension 3, it can be embedded in a Euclidean space of at most 14 dimensions. Why so many? I have no idea. If it's a four-dimensional Riemann manifold, you might need as many as 19. So this is pure mathematics. You put on a white coat and gloves and cross along. Well, we're now actually not that far from the math department. Anyway, so the metric then is, as I said before, if the point moves by this amount, then the squared distance is going to be related to the dot product of the basis vectors. And these dot products are going to be just simply just the ordinary dot products of however many dimensions this space happens to be. So it's just a dot product, and it's automatically, the metric is automatically a symmetric rank 2 tensor. And because the tangent vectors are covariant vectors, the metric tensor, which is the dot product of the tangent vectors is a rank 2 covariant tensor. ds squared is just dp dot dp, and that's just the ordinary meaning of distance in Euclidean space. And so it's invariant tensor form is gi k dx I dx k, but that just follows from what these basis vectors do. So I think that this way of looking at Riemann surfaces as embedded in Euclidean space is I think this is the right way to think about general relativity, and I think it demystifies it. It's of course possible to say, well, we don't need any of that. We can just speak of the vector of the metric itself and ignore the possibility of embedding. But well, for one thing, you don't even know for sure why the metric should be symmetric if you don't have this embedding viewpoint. On the other hand, you could arrive at the symmetry of the metric by saying, well, the only thing a metric has to do is to give the correct quadratic separation or squared distance like this. Then if you say that, well, it's automatically symmetric. And examples of embedding are the sphere in Euclidean space, and all right, let me now go on to, I'm skipping a little bit because I went through a lot of this yesterday. Metric tensors of semi-Riemannian manifolds. And of course, what you know is our universe has time, and just between you and me, I don't think we really understand time. I mean, space is one thing, you know, that's space. We don't see time. We just are sort of floating through time. So time and space are not the same. Despite the fact that time is a coordinate. Anyway, the metric of special relativity has one minus sign. That's to take account of time. And the squared distance then is in special relativity, it's the ordinary distance squared minus the time squared, the difference in time squared. So the definitions are a semi-Euclidean spacetime of dimension d is a flat spacetime with a metric that's a dot product with L minus signs and d minus, what is this, L minus signs. And okay, there's a mistake there. That if it's L minus signs, then it's d minus L. So maybe I should say U minus signs. Anyway, let me just change that. There's obviously a mistake there. D minus U, D minus L. What's a good letter? Is it U? Well, let me quickly change this U to, or this L to a U, and we can then worry about, so that's actually a mistake. That is a typo. So U minus signs and D minus U plus signs. And a semi-Riemannian manifold of dimension D, well, it's a spacetime that looks like semi-Euclidean spacetime and locally looks like semi-Euclidean spacetime and is smooth enough for these derivatives to exist, the derivatives that define the tangent vectors to exist. And what people showed more recently than Nash's theorem is that every semi-Riemannian manifold can be embedded without change of shape. in a semi-Euclidean space-time sufficiently large, and that's U and D. So let me fix that. I don't know. I'll just move that. Where is this sufficiently large? Somehow this thing isn't, it normally is supposed to get me exact. So every there. So this is a U, right? So, and then what's also been proven much more recently is that every physically reasonable semi-Riemannian manifold with one dimension of time, 3 dimensions of space, can be embedded without change of shape in a flat semi-Euclidean space-time of 1 temporal and at most 19 spatial dimensions. These 19 spatial dimensions, that's pretty strange. I've often wondered whether the higher dimensionality required in supersymmetric string theory is related to this result. Anyhow, the semi-Euclidean d-dimensional dot products of the tangent vectors of an n-dimensional semi-Riemannian manifold define its metric. In other words, GIK is basis vector EI dotted into basis vector EK, and then we have U minus signs and D minus U plus signs, and it looks like this. And once again, the metric is symmetric. So the way I think of the metric, it's always symmetric. In standard general relativity, the metric is always symmetric. There are offshoot versions of relativity that are different, and I'm not going to discuss them. I've never studied them. All right, the squared pseudo distance or line element between 2 nearby points is the inner product of the small change dp with itself. So that's what I've been saying all along here. I'm just writing notes to myself, things I should change. Okay, so examples then of this, of the semi-Euclidean or semi-Riemannian manifolds. Manifold just means smoothly curved space, basically, where in which you can have coordinate systems. So what's basically needed for special relativity. And what you can do, it turns out that there are very few maximally symmetric spaces or spacetimes, and there are 2 maximally symmetric 2-dimensional spaces or spacetimes. One is the hyperboloid, the other one, of course, is the sphere. And as I said last time, the sphere, it's points x, y, z, where x squared plus y squared equals z squared minus r squared. And so it has these polar, you can give it polar coordinates. If you have them, put a minus sign here for the metric, then you get these inner products, and your metric then is g theta theta z theta dot e theta. E theta dot e phi is 0, and g phi dot g phi is, or g phi phi is e phi dot e phi, and that's that. And so this is the metric in sensible coordinates. If you change to these fancy coordinates, you get an expression that looks like this. And this is very much the way people write the metric of the metric used in cosmology. Basically, in 3 dimensions, if you look at 3-dimensional manifolds, there are only 3. Well, when I said maximally symmetric 2-dimensional manifolds, I left out the obvious one, the plane. So there are 3: the sphere, the plane, and this hyperboloid. If you go to 3-dimensional space, there are 3 Riemannian manifolds that are maximally symmetric. One is the surface of a sphere, the 3-dimensional surface of a sphere embedded in 4 dimensions. The other is the 3-dimensional analog of the hyperboloid. And the third is just 3-dimensional Euclidean space. And what cosmologists have found out is, and of course, one thing that we always knew was that 3-dimensional Euclidean space was a good approximation to space, at least locally on ordinary distances. Now in cosmology, it appears that it's also true that 3-dimensional Euclidean space is basically the, experimentally at least, it's what the real universe looks like. Anyway, the metric is non-singular. We can form an inverse, and the inverse metric is then written as G upper IK, and the idea is G upper IK times G lower KL is going to give you the Kronecker delta, or the identity. And you can show that it transforms as a second-rank tensor. And then in special relativity, remember, in special relativity, we'll say something like Pi is eta ik, P lower k, and P lower k is eta KL, P upper L. So you, in special relativity, use eta, where of course eta is -1, 1, 1, 1, to raise and lower indexes. In general relativity, you say Pi is GI K PK, and the same thing is P, say lower k is GKL P upper L. So you raise and lower indexes in special relativity with eta, in general relativity with G, and it's a 4x4 matrix that describes the gravitational field. So you can, one index that you can raise is the index of a tangent vector, and it becomes then a cotangent vector. And the dot product of cotangent vectors gives you the inverse of the metric. And if you take these outer products of tangent, cotangent, dotted into a tangent vector, using whatever the dot product is, whether it's all plus signs or some minus signs, you have to use whatever is correct. You then get a Kronecker delta and EI. So you get, so this is the identity. If you write it the other way, the cotangent vector, tangent vector, do the same dot product, you again, since the cotangent and the tangent vectors are orthonormal, you get EI. I maybe didn't mention that, but the cotangent vector then is GIKEK, and consequently, if you take the dot product with EL, well, EK dot EL is GKL, but then this was the inverse of that, and so you have the Kronecker delta. Okay, so covariant derivatives. Now, what covariant derivatives are is they're things that transform like covariant vectors. And so what you have then is that the covariant derivative of a contravariant vector, that's got to be something that transforms as a mixed second-rank tensor with a covariant lower index, a contravariant upper index. And because we're using these basis vectors, I think we have a natural way of doing that. Namely, we take the contraction of the contravariant vector with the covariant basis vectors and make a scalar. The derivative of that is a covariant vector, and that gives us then these two. When the derivative acts on the two parts of V, you get these two terms. And so that's a covariant vector. And we can say its kth component is the dot product with the kth cotangent vector. And that's a nice thing to do, because when EK hits EI, you just get delta KI, and that gives us VK, the Lth derivative of VK. So if everything were flat space, this would be that, which is what we'd expect in the first place, and we could forget about this. In curved space, you've still got EK dot whatever this is, and that gives us this expression, this extra expression here. This thing is called the affine connection, and people also associate it with a name that's hard to spell and hard to pronounce, for that matter. Anyway, the bottom line here is that the covariant derivative of a contravariant vector, which can be written as VK semicolon L, is the ordinary derivative of the kth component plus this dot product of the cotangent vector with the Lth derivative of the tangent vector. And now we sum over I. And this is, and the affine connection enters like that. And one finds that the cotangent vectors have zero covariant derivatives, and one finds the tangent vectors also have zero covariant derivatives. The way in which the affine connection changes, it has three indexes, so it's got to change with three of these partial derivative things. But it's not homogeneous. If we could forget about this term, we'd say it was rank 3 tensor. But you can't forget about this term. And in fact, this term is necessary to make this thing a covariant derivative. If you didn't have this, it wouldn't be covariant. And that's also why in quantum mechanics, you have something like D minus, well, if I put in the units, E over CA. And so in particular, if we just do the 3-part, it's D grad minus E over CA. And there's actually a 1 over I here. Make this Hermitian and that's Hermitian. So this, and the reason is that A prime is equal to, these are vectors, I don't know, plus or minus E over C grad. I'm where this thing is a scalar. So this is ordinary E and M, and or E and M in the language of quantum mechanics. What's lies behind this is that your charged field is E to the plus or minus IE lambda psi. And what also is very important is that since there's a gradient here, this thing depends upon space or space-time, in fact, space-time. And so it looks like this. So this is the analog of a gauge field connection. And just as the electromagnetic field that is the 4-vector potential AI or AK, transforms, is a gauge field, so too this affine connection is a gauge field or a gauge connection. And we can also define covariant derivatives of covariant vectors. We do the same thing. We make this scalar, but now we make it with cotangent vectors. And so we just say, take the derivative, and then to get rid of all the vectors, take a dot product with a basis vector EI. That then gives you an EI dot EK. That's a Kronecker delta. So we get the standard derivative, which in the absence of gravity would be the whole story. But then we also have EI dot EK comma L, and that's this thing. But in something that I went through yesterday, but I think I skipped today, this EI dot EK comma L is the same thing as EI comma L dot EK. And the reason for that is that EK dot EI is delta KI. This is a Kronecker delta, and so the nth derivative of this is 0. So that is 0, and that is then EK comma L dot EI plus EK dot EI comma L. So that's why you can go from, where is it? EI dot EK comma L, that's this one, which is this one, and you can go over to this one, which is this one. So that's the covariant derivative of a covariant vector. And in particular, if you apply it to the tangent vectors, you get 0. And the way in which covariant derivatives act on tensors is they're defined to act so as to make the covariant derivative a derivation. And a derivation, just in general, so let me write it like this. A derivation on AB is the derivation on A times B plus A times the derivation on B. And so in particular, the covariant derivative of two contravariant vectors is the covariant derivative of the first times the second plus the first times the covariant derivative of the second. And that generalizes to arbitrary vectors, arbitrary tensors, I mean. So you have, well, I mean, now, if you apply this to, in particular, the GIK, you find that the covariant derivative of the metric vanishes, and that's important. I think we'll go to that next time. So let me just write it down. DL GIK equals 0, so we can start there Tuesday. There's no class tomorrow because tomorrow we have one of the several commercial holidays in the United States. So I wish you all a happy Thanksgiving, a peaceful weekend, and look both ways crossing streets, and wear a mask if you're indoors with people who aren't vaccinated, and for God's sakes, get triply vaccinated as soon as you can. It's important. So I'll say good night now since we're out of time. And So send me an email and tell me, am I going too fast, or I can't imagine that I'm going too slow. Also you might say, well, do you want me to continue with general relativity after Thanksgiving, or do you rather see something else? There's a lot of stuff in the rest of the book. All right, I'm going to stop recording now. So goodbye, everybody.